The Laplace transform kernel function is e raised to minus alpha t. Hankel transform k of alpha t is equal to t jn of alpha t. Mellin transform, the kernel function is t raised to alpha minus t. Hankel transform is used in order to solve considering potential problems which involving cylindrical coordinate system. Laplace transform is used to solve differential equations, mainly electrical circuit, etc. Now, among all these integral transform, Laplace transform is the most commonly used one. So, we will deal with the Laplace transform in detail. Laplace transform of a function is notated like this: small f of s. This is the Laplace transform of function f of t and is notated as L, italics L, braces f of t, which is equal to integral 0 to infinity e raised to minus st f of t dt, where s is a real number and it should be greater than or equal to 0. We cannot calculate the Laplace transform of every function. There is some limitation for the selection of Laplace transform of a function. The first condition is the interval we are considering in the case of Laplace transform is it should be between 0 and infinity. That means if you are considering two functions having identical behavior in the range between 0 and infinity, but they are behaving differently in other region, if we are taking the Laplace transform of this function, these two functions, these will be same. So this is one of the limitation of Laplace transform. Now, in order to get the Laplace transform of a function, the infinite integral of the function f of t dt, integral 0 to infinity f of t dt, need not exist. Or as t tends to infinity, f of t tends to infinity. Some certain functions are of this form. This function we cannot find out the Laplace transform. So the condition for getting Laplace transform as integral modulus of e raised to minus s0 t f of t should be less than or equal to m, where s0 is a positive number and m is a constant. If the function obeys this condition, the Laplace transform of the function f of t can be calculated for s greater than s0 only. For s greater than s0 only. For example, function e raised to t square, if you are considering a function f of t is equal to e raised to t square. This function does not obey the above condition. Therefore, the Laplace transform of function of this form, e raised to t square, e raised to x square, these function does not, for these functions Laplace transform does not exist. Another thing is, as t tends to 0, if f of t has strong singularity, For example, f of t is equal to t raised to n, where n is less than or equal to minus 1, for n is negative value. When t is equal to 0 for this particular function, we know that f of t is equal to infinity. That type of points are called singular points. So singularity exists for this particular function, and the Laplace transform of this type of function also does not exist. Now, in the properties നോക്കാം. First property is linearity. For that we are considering two functions. For these functions there exists Laplace transform. It will be f1 of t and f2 of t. And if you are considering another function which is a linear combination of f1 and f2, let it be written like this: f of t is equal to c1 f1 of t plus c2 f2 of t. And if you are considering the Laplace transform of this particular function, c1 f1 of t plus c2 f2 of t, it will be equal to c1 Laplace transform of f1 of t plus c2 Laplace transform of f2 of t.